Welcome back to another video in this series on design patterns for object-oriented languages. In this video, we are going to talk about the state pattern. So the state pattern is a way of managing state. Or rather, the state pattern is a way of building a state machine in a sort of object-oriented fashion. And if you're not familiar with state machines are actually a well-studied concept in computer science that is heavily studied theoretically. And in some sense, you could say that many of the state machines are memoryless machines. In other words, machines that make decisions on the basis of where they are currently or in what state they are currently, and not based on how they got there. And that's how we will use the state pattern. We will use the state pattern to say that you have some object that will behave differently depending on what state it is. It doesn't matter how it got into that state, but depending on what state it is, it will do a bunch of different things. So we're not going to talk in depth about the sort of theoretical part of state machines, but I'll suggest a few links in the description if you think that it sounds fascinating. And if you have suggestions on interesting videos or playlists on the concept of state machines, do share that in the comments. And I'm sure others will appreciate that massively. And also, if you want us to talk about state machines, ping me and then maybe we can talk about it at some other time. But anyways, here's how we can denote state machines. So when we draw state machines, we say that there are states and then there are transitions between states. So here's a state, and here's a transition between these two states. And then maybe we can have a transition back like this, and then maybe a transition like this. So if this is state A and this is state B, then from state A you can move to B, and from state B you can move to state A. But from B you can also move back to state B, and so forth and so forth. And then we would have like a starting state and an ending state. So let's look at a state machine for a very simple example. Imagine the subway, a tram or a metro or something like when you get onto public transportation and you have to pass through a pay gate. So just think of it like this, like let's say there's a fence here and a fence here. You are here and you want to pass through here, or you want to pass through this fence, and the only way to pass through this fence is through this opening, and maybe there's this sort of swivel thing here. So when you walk through inwards, you walk on this side, and when you walk outwards, you walk on this side, and then this thing spins in sort of this direction, right? So when you come here, you push through that thing, right? And you can sort of swivel through it. I'm not sure what that's called, like a rotating door kind of thing. Anyways, I think you see the point. As like when you grab a metro. Clearly, usually you would have many of these and so forth, but whatever, let's just think about one. And let's think about this as a machine. This is sort of classical, like when we talk about state machines, we tend to talk about real-world machines that are really simple, like a turnstile, or a gumball machine, or something that's sort of easy to conceptualize because you can think about the mechanics inside of it, or a parking machine or anything like this. Anyways, so if you're in a subway, then these turnstiles are there because they want to automate the fact that you need to pay in order to ride the tram or the subway or the metro or whatever. So let's say that here next to it there's this sort of payment machine, and maybe it has like a light here that's currently red to indicate that the turnstile is closed. So what we do is that we take our subway card and then we swipe it, or we place it. Let's not say swipe, let's say we place it on top of this. Boop. It beeps and then we walk through it, right? Assuming we have funds on the card. So let's model this kind of turnstile with a state diagram, or as a state machine. So which states do we have? Well, the turnstile can be locked. So at least there is a state called locked. Yeah, I mean, we could have called it closed, but let's call it locked. It's locked as in we can't move it. But then there's another state which is open. So in other words, what I mean is that if it's locked and then I try to pass through, I can't pass through because it's locked. It stops, it doesn't spin. And if it's open, I can't spin it, right? But the problem is that we don't want it to indefinitely remain locked. And we neither want it to indefinitely remain open, because if it's always open, just everybody can simply just pass through and nobody has to pay. So then we have transitions. So if it's locked, you can somehow make it open. And if it's open, you should somehow be able to make it locked. And then we have to ask ourselves, what are the events or the actions that cause these transitions? So when you go from locked to open, that happens if you pay. If you put your card and then you pay and you happen to have sufficient funds on the card. So let's say, to keep it simple, let's say pay OK. So if the payment was OK, then we transition from locked to open. And then the user, the person using the turnstile code, passes through. So let's call that pass or push or enter. Let's actually call it enter. So if we enter, then since we've now entered, we've only paid for a single person. That means since we've now entered, we need to transition from having the turnstile open to now being locked. Actually, let's call it closed. This sounds strange if we say open. Closed. So we go from open to closed. But we said that when we pay, we go from closed to open if we have the necessary funds. If we don't have the necessary funds, what happens is that when we're at closed, we are trying to pay, but we don't have the funds. So let's here say pay, fail. Okay, failed maybe. So if the payment failed, then when it's closed and we try to pay, then we simply stay in the closed state because the payment failed. The payment, it's not enough for me to just try to pay. The payment has to actually go through. The payment has to actually succeed, has to be okay in order for the turnstile to go from the closed state to the open state. And actually there's another interesting thing here. That thing is that when we are in the open state, you can also try to pay. What I mean is this. Now this light here is red, but as soon as you pay and the payment is okay and the turnstile turns open, then maybe this light turns green. But what if you then take your card and place it on the reader again? And let's say that you then still have sufficient funds. So that means that in the open state, you can also receive a pay okay message. But that shouldn't matter. If you try to pay again, clearly your funds shouldn't be withdrawn, like the payment shouldn't go through, but that's something we can't really capture here, or at least without adding more complexity. So within this simple diagram, we're not capturing that, but at least what happens is that we stay in the open state. It's not like if you pay once and it opens, and then you decide for some reason to try to pay again, it's not that it suddenly should turn closed. You've already paid and nobody has passed through, right? That's the key point. We haven't run enter yet. We haven't received the message. We haven't executed the action. We haven't received the event enter. Not until we receive the event enter should we actually move to closed. So if you just stay there and you pay and pay and pay and pay and pay, it doesn't matter, it stays open. And again, of course, you shouldn't withdraw funds from the card. So if we then receive pay okay, it should still stay open. Now what's interesting about these sort of state diagrams is that if you think about it, we have a number of events or actions, and then we have a number of states. And that means that we can draw this sort of table where we enumerate all of the different combinations. So we can say that what we have is that we have a number of states, and then we have a number of actions. And let's count these. We have 1, 2, 3 unique actions, and then we have 2 states. So let's draw these out. We've got enter as an action, pay okay as an action, and pay failed as an action. And then we've got the states closed and open. And maybe I should put the headers this way to avoid any confusion. Actions and states. So the question we ask ourselves now is that if you are in this state and you are supplied with this action, in which state do you then end up? Or in which state do you then transition to? And we can show that by simply looking at this chart that we drew. So if you're in the closed state and you receive the action enter, then actually we immediately realize that we didn't draw that before. So we haven't actually drawn all of the arrows necessary. And if you just count that, what we have is that we need 1, 2, 3, 4, 5, 6 arrows, 6 transitions. But here we actually only have 1, 2, 3, 4. So we're missing 2 transitions. Number 1 transition that we're missing is that if the gate is closed and somebody tries to enter, what will happen? I mean, we talked about that before, but we forgot to model it. Well, what will happen is simply just this. It's closed. We try to push. We try to enter. We try to enter through the turnstile, but because we haven't paid, and we know we haven't paid because we're in the closed state. Again, remember, there is no memory in this machine. It's just that if I am currently, right now, in the closed state, that means I have not been paid to allow somebody to enter, which means I should stay in the closed state. So I am in the closed state. I receive the action enter, but I then transition back into the same state, back into the closed state, because I'm not allowed to allow someone to enter if they haven't paid. I'm in the closed state and I should remain in the closed state. So then we know that if we are in closed and we receive the message enter, we should stay in the closed state. So let's here say that the result here is closed. Next one, what if I'm in open? I'm in the state open and I receive the message enter. I receive the event enter. Somebody tries to enter. I'm in open, I receive the message enter. Well, I should transition to closed. And again, we're missing some pieces here. Like clearly what will also happen is that the user will actually enter. Like if this is a login system, the user will actually be logged in. Or if this is a turnstile, the user will actually move to the other side of the turnstile. So again, we're not capturing all of this, and maybe we should think about that as a state machine of the other thing, or maybe we just shouldn't capture that here and worry about that in terms of code. I mean, we're drawing this now to try to understand how we can use the state pattern, not necessarily with the intent of using state machines to describe a program to 100% or to describe a program completely. But again, if you are interested in that, state machines are outrageously interesting, so check out some of the links in the description. Moving on. So what we said now is that if we are in the open state and we receive the message enter, then we should move to the closed state. So we are in open, we receive enter, and we move to closed. And again, something more should clearly happen, which is that the user should be let through or logged in or whatever it is that we're actually modeling. Next one. What if we are closed and we receive pay OK? So if the turnstile is closed and I receive the message, the payment has now gone through, which then happens if somebody puts the card and the payment is successful. Well, if we receive the message pay OK, then as we see here in the diagram that we drew before, we can see that if I'm in the closed state, I receive payment OK, then I should move to the open state, clearly. So then let's say the closed state with an OK payment moves us to the open state. And let's just immediately continue. What happens if I'm in the open state and I receive the message pay OK? So I'm in the open state and I receive the message pay OK. And that's what we talked about before as well. If you pay, the turnstile opens, but if you then pay again while it's open without passing through, right? I'm on this side, the turnstile is here, I pay, it says green, open, I won't pass, but instead of passing, I'll just put my card again, boop, right? Maybe it doesn't beep because it's like, well, stop trying to pay, you've already paid, right? But I tried to pay and my payment is actually successful. If that happens, it should remain open. You can also, I mean, it's a bit funny that we have these events that are pay OK and pay failed. It helps in my mind, and maybe it helps in your mind. You can think about it this way. Maybe these are asynchronous events. So maybe the thing is that initiating a payment is actually one event, and then we get a response back. And we'll add that complexity in just a moment. But for now, think of these as asynchronous events. I mean, the reason I'm saying that is that it feels that the wording is a bit odd, that suddenly you would receive a message which is pay OK. But again, that happens if I'm on this side of the turnstile, I've paid, I haven't passed through, but then I pay again and that payment is okay. Or again, the payment wouldn't be okay because it wouldn't necessarily be processed, but again, think about asynchronicity. Maybe I'm using some kind of third-party payment system, payment processor that calls me or sends me events. And maybe for some erroneous reason, like for an incorrect reason, they send me one of these payment OK messages. And then I have to think about, okay, how does my application handle this? How will my application handle the fact that we get this message even though we were not actually expecting this message at this point in time? Right? Because we were now in an open state and we're not expecting to receive, this payment was okay. We're like, what payment? Why did you send me this? But if it happens, then we shouldn't suddenly close the turnstile, as we talked about before. If somebody tries to double pay, or if there's an error with the service that sends us payment okay and payment failed messages, then we shouldn't suddenly punish the user for that. The turnstile should remain open until somebody passes through. So that means that if the state is open and if we receive the message pay OK, we should remain open. So the result here is open. Similarly, let's jump to this cell. If we are open and we receive the message pay failed, the same thing should happen. Again, we are not expecting it to happen. but depending on how we architect different pieces, it hypothetically could happen. So if you are in the open state, again, I've come up to the turnstile, I take my card, I blip my card on the blipper, there's probably a more correct term for that, but never mind, and it says, okay, it turns green, the turnstile is open, but I'm not passing through. What I do is I take my card again, and then I blip it. But this time I have no funds because I just paid for opening the turnstile. I paid for my trip just now, and those were my last funds, let's say. So now that I blip it the second time, it will reject my payment because I have no funds on the card, but I've still paid for one entering. I've still paid for one trip, and I shouldn't be punished for just putting it again. Like maybe as a user, maybe I do it by mistake. So when I do blip the second time, the turnstile should still remain open. Again, the key point is that we only move from open to closed whenever somebody actually enters. Regardless of all of this other stuff, and regardless again of the history, if I'm in the open state, unless somebody has entered, the turnstile shall remain in the open state. And as soon as someone enters, zoop, it just turns closed immediately. You've paid for it, somebody has walked through, now it's closed. So in this state, if we're in the open state and we receive the message pay failed, even though it's a failed payment, we should still remain in open. Because again, if we are in the state open, somebody has paid. Inevitably, the only way to get to open is if we have received an okay payment. So there is a payment and nobody has used up that payment yet. And now that we added this pay failed, we of course need to draw this arrow as well. So let's add another arrow here. This left one is pay okay, and this right one will now be pay failed. By the way, there are also different types of state machine diagrams. So what I could have done with this okay and failed notion is that I could have added a transition that was sort of conditional, where both of these are based on receiving the action pay, but one is with the status okay and the other is with the status failed, for example. But I think it's just easier to stick to separate messages. And now let's add this last pay failed arrow that we drew here on the right side to the table over here. So if we're in the closed state and we receive the message pay failed, then we stay in the open state. And that's it. So now we have that transition table, and we essentially know that regardless of which state we are in and regardless of which action we receive, we know exactly what to do. And this is the power of using, well, firstly state machines, but in object-oriented programming using the state pattern. So it forces you to not wildly mutating your state by mutating different properties of some object that you have, but instead mutating a single thing, which is this state variable. You have a state instance variable that says whether you are now closed or whether you are now open. And this state variable will not contain an enum or a string or an int defining which state it is in. It will contain its own state object, and this state object will implement all of these different methods. So maybe what you're seeing is that what we are doing is that we are replacing a conditional with polymorphism. So if we didn't do the state pattern, what would we do? Maybe we would have a boolean that is like is open, and it's equal to either true or false. And then if we receive the message enter, let's say, and I'm in the turnstile object, so in the method enter, in the turnstile object or in the turnstile class, if my instance variable is open is equal to true, then what I should do is that I should set is open to closed. Because again, it was open, I received the message enter, and it should now be closed. So I would say something like, if it is open, then is open is now false, because we've now entered. And then of course here, ... I need to do that other stuff that I would have to do for making sure that the user is now entered, or well, whatever we were intending to do actually. But there's a huge problem with this way of doing it, which you can probably see. And that is that if we have the methods enter, pay okay, and pay failed, then we need to duplicate this conditional logic for all of these methods. So we need to ask if it's open whenever the enter method is called, whenever the pay okay method is called, and whenever the pay failed method is called. And what's worse is that now we only had closed and open. But what if we also had pending? So what if pay happens first as a state? So what if there's closed, there's open, and there's pending? And pending is essentially when the payment is being processed. So actually, let's call it that instead. Let's say that that state is processing. So that means that closed takes us to processing, And processing may take us to open or may take us to closed. But that also means that we need to handle the messages pay OK, pay failed, and enter in this third state, which is processing. So let me see if I get this right. That should mean that let's add the third state here as well. I'll just write proc period as an abbreviation of processing. And let's extend these lines like this, and then another line here. That means that the number of different implementations that we need is essentially 3 because of 3 states times 3 because of 3 messages or 3 methods, 3 functions. So what we're saying is that if we're not just thinking about the positive cases, if we're not just thinking about the thing that we actually hope will happen, if we think about all of the cases that could happen, well, we could receive any of these 3 messages at any point in time. And that means that we could receive any of those 3 messages in any of these 3 states. And now clearly, these states we made up. So if we think about the problem, we could have ended up with different states. This depends on how we want to model it. But if you just think about it, the states that we now have are quite intuitive. Like the notion of the card being processed, having to wait for the card to be processed, I guess is kind of inevitable. Like unless you have some kind of cache solution where you put cache inside the machine, but even then maybe there has to be some weighing of the cache or laser checking of a bill or something like this. Like there's probably a delay. And during that delay, people can fiddle with the machine. What happens if I push the turnstile while the machine is processing a payment, while the machine is in this sort of idle or in this sort of waiting state? And again, now we are talking about a physical device, about the physical turnstile, because it's just easier to think about them, and probably everyone has seen such a thing. But of course, this could have been anything. This could have been a network request. So a network request is maybe unfired, it's fired, and it has returned something. Or maybe if you think about promises, you have some action that you want to perform, and maybe initially it's unperformed, then you ask it to perform the action, and then you're in this sort of waiting state where the promise has not yet resolved, and then it can either resolve or it can be rejected. And so you can also think of this concept in terms of states. So there are many, many things that we can, if we think about it, turn into states and then start drawing one of these transition diagrams that explicitly specify that whenever I have this particular state, I want to handle this particular action in this particular way. So in some sense, it's a very safe way of approaching programming, because suddenly you start to think about, well, okay, this is again what I hope will happen, but what if this other thing happens? And then it's a way of making sure that you're not missing any cases, like we did in the beginning. So where I was going with this 3 times 3 is that 3 times 3 is 9, which is essentially the number of unique combinations of states and actions, and thus the number of cells that we have in this table. And even with state pattern, we need a separate implementation for each of these 9, because that's the point. The point is that we need to specify whatever happens in every combination of a state and a message. But if we didn't use the state pattern, either we would, it's actually possible that we might not have to write code for all of the states, because we might bundle some up and make them implicit rather than explicit. But there's a high risk that we might miss some states. And either way, what we would have to do is that if you think back when we wrote this piece of code, here we actually only had a single variable. We had isOpen. So then it was kind of easy, because then every action had 2 paths. It was kind of obvious. If you call the method enter, then you know that the turnstile is either closed or it's open, and we have to do different things potentially depending on which one we're in. That when we have the notion of only closed and open, this is kind of easy to model even without state pattern, because we only have 2 states. We essentially have a bool and we have 2 paths. But if we suddenly also have processing, well, suddenly it's a bit difficult, because what are we going to do? Maybe we have I can't remember what that's called, but like a 3-value bool, but that's probably not intended for usage like this. So suddenly now we need something that holds 3 potential values. So maybe now we start to go into craziness like having a state variable that contains one of 3 constants or one of 3 enums. So one enum that says closed, one enum that says open, and one that says processing. And then we if over that, or maybe now we start to write a switch case. So we say switch, if the state is equal to open, do this. If it's equal to closed, then do this. If it's equal to processing, then do this. Or we could even try to sort of wing it without a case statement and without a state variable. So maybe we would try to say something like, there's the notion of closed or open. That's one variable, that's one bool. And then there's the notion of processing or not processing, and that's another bool. But think about it, that actually means that we have more states. That actually means that we now have 4 states. So let's draw one of these sort of quadrant diagrams, or I'm not sure what they're called, but you've probably seen these. So the combinations that we have is essentially that this variable can be true or false, one of the variables, let's say is open, and then we have is processing, and that can also be true or false. So that means that we can have true true, true false, false true, or false false. So in other words, this would be is open and is processing. And then this would mean that it's open but it's not processing. And this would mean that it's not open but it's processing. And this would mean that it's not open and it's not processing. And this is kind of a different thing, right? Because suddenly we have this notion of that processing can happen when the turnstile is open or when it's not open. But actually, we don't even want the scenario that it's open and we're waiting for an answer. So we don't want the state that it's open and it's processing. So that's actually a completely unnecessary state. And now, again, this was with only 2 variables. So you can probably see how if you would introduce more variables, this would sort of explode. Clearly, both of these scenarios explode in terms of complexity as you add more states or as you add more methods. But not doing it using state pattern can quickly become difficult to reason about. Like suddenly you have to keep track of which variable combination you have to check. And the really dangerous part is that you have to do this for every method. So what we didn't say is that when we wrote up this, if is open, so like when we have this branching in every method, when we have this checking of the current state or checking of the current variables to determine what kind of state we are currently in, this logic, this piece of the logic, the checking, the branching, has to go into every single method that we have. So in all of these different methods, we need to check, we need to determine what's the current state that I'm in, compute it, and then we can determine what we need to do. And again, if you have many branches, this can quickly become quite difficult to reason about. And then I would say potentially quite dangerous because it's difficult to reason about, so it's error prone. Whereas if we use state pattern, it's in some sense much simpler because we just devise a number of different states. We give them names and then we can reason about it. We say, well, if I'm in this state and I receive this action, what's the logical thing to do? What's the best thing I can do, right? Because again, we would hope that everything works, but sometimes things are just messy. So if we're in the processing state, for example, and we never receive a message back from the payment processor, maybe then we have some kind of timeout. So after some timeout, we automatically move from the processing stage. Sorry, we didn't draw the processing state here, but let's say we have a processing state. We automatically move from the processing state back to the closed state because we say, okay, we're no longer processing. We are now accepting another try from you. Because if we are in processing, we should probably not accept more tries from the user putting their tram card or metro card on the reader, because again, that would be equivalent to how we would not do that in the open state because it just doesn't make any sense for them. We're already processing something for them, so they simply have to wait. So maybe then, if we don't get a response back, we simply do a timeout and move back to the state closed. And when we're then in the state closed, maybe then later suddenly we do receive a message back. So maybe now the card processor instance or remote service or whatever that is manages to give us a response and says, the payment succeeded. That's actually a pretty interesting scenario because if we're using this state model without the processing, when we only have closed and open, then if we do receive that pay OK message, then we would just say open. Right? Because we don't know that came from like a long time ago and there was a huge delay. So then we would just, boop, it would randomly open for someone else, not randomly, but like it would open for no apparent reason from the outside. But if we have this extra processing state, then as soon as we've left the processing state, we can say that when the gate is closed and you receive an OK message, don't open. Because if that happens, that means that this happened for an erroneous reason, for an incorrect reason. You should only open if you're in the processing state. Then you should move to open. So hopefully you can see how that becomes a lot easier to reason about. Let's actually add this processing state to make sure that we're all on the same page. So let me remove this arrow that the payment OK from close to open, that the payment OK takes us from close to open. Because as we just said, this should probably not happen now. So let's say that we now have this processing state, and again I'll write proc period to abbreviate processing, and closed can take us to processing, processing can take us to open, but processing can also take us to closed. And let's think about when these things happen. So processing happens when we need another thing, we need another action. We don't just have pay OK and we have payment failed, we have payment initiated. So let's just call that pay. So if we initiate a payment, then we move from closed to processing. If the payment failed, let's say pay fail, then we move from processing back to closed. However, if the payment was okay, pay OK, when we were in processing, then we move from processing to open. And those are 3 methods, but we added one now, we added pay. And since we had 3 here before, that means that we now have 4, so we're actually missing one. And the one that we're missing is enter. And then, of course, if you at processing try to enter, what should happen? Well, we should stay in processing, enter. We probably don't want to punish the user, for example. I mean, clearly we don't want to move to open. Just because they're processing a payment, that doesn't mean that they actually had the funds to pay for entering. So we need to wait for the processing to finish. But we can't just go back to closed, because that wouldn't make any sense either, because then we would punish the user for trying to push while they're waiting for a payment. So we need to wait for the payment and we need to stay in processing. And then, now I'm not modeling that, but again, if we had a timeout, maybe we would have a timeout that takes us back to closed. Which again would then mean that if we do receive the payment OK message later, when we were in closed, we wouldn't actually enter because we've now removed this arrow from close to open. And of course, sorry, since I removed that arrow, we need to redraw it again. So pay OK. If pay OK happens when we're closed, then we shouldn't actually open because the user is probably gone because we've had a timeout. But also, I mean, now I just realized that this also means that we should maybe refund, that we should maybe refund the user for this payment because we've just accepted a payment without actually opening the gate. So I mean, it depends on your scenario. You might model it differently. Maybe we would move from this payment OK into some kind of refund state where we're trying to initiate a refund and so forth. But anyways, hopefully this feels kind of clear. And then of course, now that we added the state processing, what we did here before was that we added processing here into this table of states. And then since we then also added the method pay, we need to add the extra column here, pay. But because I'm running out of space, I'm not actually going to do that. But again, since we changed the state diagram, we now have to change the table as well. So one example was that when we were in the closed state and we received the message pay OK, we previously moved to open. So when we were in the closed state and we received the message pay OK, we moved to open. But that's no longer the case because now we stay in the same place and we remain in closed. But and so forth, we would have to need to fill this in. If it's not already clear, let me just mention a tiny short example of why this is very useful. So think about this light here, right? Here we have this red light. So let's say that we want this to be red when the turnstile is closed. So what we're trying to avoid is users being angry and standing in front of the turnstile and pushing it even though it's closed and like wait for it to open or like, why are you not open? And so forth. Or conversely, maybe standing in front of it and they're assuming it's automatic or something like that, and they're like, well, why are you not spinning? Something like that. So maybe then this light has 3 states. So maybe it can be red, it can be yellow, and it can be green. So it's green if it's open, it's yellow if it's processing, and it's red if it's closed. So that's super simple in using the state pattern. So that just means that maybe we have another method which is get status or something like that. And if we are in the closed state, we return red. If we are in the open state, we return green. And if we're in the processing state, we return orange or yellow, sorry. And interestingly, we talked about this thing with pay. What we could actually do now is that if we wanted to, we could for a short period of time move to another state or something like that. Maybe we could find another way. But what I'm trying to point to is that maybe we would want to quickly flash red, for example, if the user tries to use the card to pay, even though we're processing. So the light is red. I don't actually have a yellow or an orange pen, so blue will have to do. The user puts the card down, the light becomes blue to indicate that it's processing. And maybe if we then place the card on the reader again, it's trying to indicate to us that hold on, don't do anything. I'm still processing. So maybe it just quickly flashes red and then goes back to blue. And maybe we would do that by either introducing another state that takes us, so when we're in processing, we get into this other state of trying to tell the user that, hey, you should please stop putting your car down, I'm actually processing, and then we go back to processing. If we're thinking about it as a simple state machine, but if we think about it more as a program where we can actually dependency inject and so forth, maybe we would do it by injecting the light to the state, and then this processing state would perform operations upon that light. So we would make the light go red for a moment and then go back to blue. And then again, as soon as we move from processing to open, the light suddenly shifts to green. And then again, we enter, it turns closed, and the light goes red. And clearly, as with all of these things, you could of course solve that using these sort of if statements and switch statements and all of that stuff. The only thing I'm saying is that with state pattern, that's probably a lot easier. And when I say easier, I mean in terms of not getting confused about whether you have narrowed down which state you're actually in correctly, or whether you have handled all of the different cases, all of the different potential states, and whether you have handled the state correctly, and just realizing which combination of different variables, of different checks, equate to what state. And of course, the fact that we have to massively duplicate all of this code across all of the methods, which means that if we suddenly introduce another state or another action, we have to just make sure to do that check in all of the different places. And if you think about it in this sense, if you're then in a statically typed language, that actually means that if you add another action or if you add another state, then you can, at compile time, realize that you're lacking an implementation for a particular combination. This is much more difficult. Of course, the compiler can't tell you if you're using this sort of switch logic. So hopefully you're seeing the value. Let's now look at the definition. So let's read the definition from this book, Design Patterns, Elements of Reusable Object-Oriented Software. By the way, this book is written by what is commonly referred to as the Gang of Four, so 4 authors. And this is sort of the classic design patterns book that put the notion of not necessarily design patterns, because the idea of design patterns was, as far as I understand, originally introduced by an architect, but that took the concept of design patterns and applied it to the realm of software, and essentially introduced this massive collection of design patterns that actually still live today. But I would assume that, similarly to the book Refactoring by Martin Fowler, that part of the exercise was to put names on things that people were already doing, which we can also see because in the book they give examples of real-world scenarios where the patterns are currently being used at that time. I mean, this is written some time ago. But anyways, what I wanted to say is that this is a great book. If you're interested in design patterns, get this book. It's the classic book, and as you can see by the thickness of the book, there's clearly a lot more stuff than what I can manage to cover in these videos, even though we cover a lot. Of course, not just from this book, but in regards to design patterns in general. But again, there's a lot more stuff in this. And if you want something which is a bit more pedagogical, then I would suggest that you get this book, Head First Design Patterns. This book simply doesn't just enumerate the patterns, but also really goes in depth and try to explain them in easy to understand manners and in, well, jokeful manners. And I mean, if you decide to get both, I don't think you'll regret the decision. Great books, and they do complement each other. Links are in the description. Moving on. And by the way, this is a playlist on design patterns, so if you're not already subscribed to this channel, now's a super good time to subscribe to the channel. But let's move on. So I'll read the definition from this book, Design Patterns, Elements of Reusable Object-Oriented Software. The state pattern allows an object to alter its behavior when its internal state changes. The object will appear to change its class. So the state pattern allows an object to alter its behavior when its internal state changes. The object will appear to change class. So think about this. We had the states here, and we have behaviors hiding under these different messages that we can send it, under these different methods. And what we're saying is that whenever the state changes, the internal state, then the implementation, the behavior of these different methods should change. And in some sense, then, you could say that, as they say, the object will appear to change its class. In other words, if it's closed and I call payOK, it behaves in one way. But if it's open and I call payOK, then it behaves in a different way. So in some sense, you could say that maybe that looks as if it changes its class at runtime. But hopefully that sounds kind of familiar. So let me remove all this stuff and let's draw up the diagram. So we usually draw it something like this. There is a context. And this context is the thing that can have states. So for us, it was the turnstile. So if we have the thing that can have states, then we must also have states. So that means that we have another thing which is called state. But this state is an interface because we want to be able to have multiple different states. And what we want is that we want the context to have states. So the turnstile has many states, but it has many different states. It has the open state, it has the closed state, it has the processing state. And again, depending on your application, these might be completely different. But we want to be able to treat them uniformly because, as we were drawing up here with the table, we have all these different messages and all of the different states need to be able to answer to or need to be able to respond to all of these different messages, need to implement all of these different methods. So that means that state is an interface of which we have a number of implementations. So let us call this concrete, and let's just say concrete state A to denote that this is the first one. And then we'll use this notation that we've been using before, sort of leaves on leaves, to denote that while we happen to show a single state here, of course you could have multiple states. And of course I'm just doing this to avoid having to draw all of these separately because then they all need separate arrows. So underneath here is another state class, and underneath that is another state class. And they don't have any relationship with each other. I'm just drawing it this way to say that there are multiple concrete states that implement the interface state. So up here we have concrete state A, then we might have concrete state B, and then we might have concrete state C. But in our previous case, these states might then be open, closed, and processing. So probably you can start to see how we will replace conditionals with a polymorphism. This is the polymorphic part. These states are all of type state or behave as type state. So the state class specifies that to be a state, you need to have a method that we here, because we don't actually know what we're modeling, we're trying to describe the pattern generally, that we here call handle. And then these concrete state methods will have implementations for this handle method. They will have specific implementations for this handle method. But of course, whoever is using this particular turnstile is not interacting directly with the states. Again, as we were reading from the definition said something like that the states are internal. So what somebody would use is that they would use the context. They would use the turnstile. They would interact with the turnstile. So here we have another method, which, for example, we could call request. And I assume the reason that people usually use a different name here than here is to emphasize that, of course, the interface of the context could be different than the interface of the state. But oftentimes, you'll probably find yourself mapping the same interface or using the same interface in the context as in the state. Not as in that they would inherit from or implement the same interface, but that the methods would potentially map one-to-one. So the reason I say that is that let's transform this now from the sort of generic form to our specific form. And hopefully you can see why I mean that they would probably map one-to-one. But before we do that, let me just mention that when we come across this diagram, it's usually drawn with some notation kind of like this, where we specify that what happens when the request method is called is that we call state.handle. So the idea here is that you have a context and it has a state. And whenever you ask it, whenever you request it to do something, when you send a message to it, it is not itself capable of handling that request. What it will do is that it will pass down the message, it will delegate down by calling this handle method, so it will delegate down to the state. And then, because we don't have a general state, or I should say, since this is an interface, the context can't have an instance of an interface. What it can have is an instance of any of these concrete classes that happen to implement this interface. So the context doesn't necessarily know exactly which state it has at runtime, but it just delegates, it just calls the handle method on that state, and then this concrete state can do whatever it needs to do depending on the state that it's currently in. These different concrete states will have different implementations of the method handle. And now, if we move to the scenario that we had before, the context, let me remove these texts. We have context and state. So the context becomes the turn style. And actually, I mean, to make it more simple, let's just call it the gate. The context is the gate. I mean, the same thing as the turnstile. I just figured the turnstile is a pretty strange word. So that's the gate that can be open or closed. So the context is the gate. And then we had state. And state we would maybe call gate state, to emphasize that it's just not any old state, it's a state corresponding to a gate. So a gate can have a gate state. And then these concrete states, no longer makes any sense to just call them sort of generic concrete states. We need to call them something specific. So maybe this one would be the open gate state. And just to emphasize, I don't mean open here as an interjection. I don't mean that as in open, exclamation mark. We simply mean that the state in which the gate is open, the open gate state. Anyways, and then the next one would maybe be closed gate state. And then the last one would be processing gate state. Or maybe to be more explicit, we should maybe call it processing payment gate state. So I'm adding the gate here to make it more explicit that it's an implementer of the gate state interface. But maybe if that becomes messy, we could just call it open state and so forth. But then let's think about these methods, request and handle. Well, let's think about handle first. Let me remove these first. And let me remove this sort of implementation thing here. So the gate could receive a number of messages, as we said. The gate could receive enter, it could receive pay, if we think about the gate that can process, and then it could receive pay OK, and it could receive pay failed. And those are the 4 different messages that we can send to a gate. So if you think about the implementation that we had down here in this sort of dashed box before, that implementation said that the gate essentially delegates whatever methods it receives to the gate state. Or I mean, previously we simply had request here and handle here, and the request method delegated to the handle method of. But now we have 4 methods: enter, pay, pay OK, and pay failed. And these methods somehow need to delegate down to the gate state. And the elegant portion is that they simply blindly have to delegate down to the gate state, because all of the logic will reside in the state, because all of the logic depends on what state we are currently in. Of course, depending on your scenario, you might want to do some things here and then some things here, so some things in the context and some things in the specific state. But in this scenario, we will assume that all of the stuff will happen in the state. And what we will do is that we will simply map one-to-one. So the enter method, when the enter method is called on a gate instance, that gate instance will simply delegate to the enter method of its state. And when the pay method is called on a gate instance, it will delegate to the pay method of its gate state. So I'll just add these methods here as well. So we have enter, pay, pay OK, and pay failed. And as we were saying before, the interface declares the existence or the need for these methods to exist. But then, of course, these specific concrete implementors of this interface, the concrete gate states that actually implement the gate state interface, they need to supply implementations for these methods, which means that we repeat them here. So enter, pay, pay OK, and pay failed. So it's essentially the same set of methods all over the place. But an important point to remember is, of course, that the 4 methods in the gate does not have to be in the gate because the gate shares some common interface with the gate state. These are completely independent, completely separate. While the 4 methods in the, for example, open gate state, those are required because this class implements the interface gate state. So because it behaves as a gate state, it necessarily needs those methods. The reason that we chose the same names is simply that we want to be able to handle each combination of a method and a state separately. So if enter from the gate's perspective would delegate to the same method in the gate state as, for example, the pay method would, then suddenly we are not able to handle all of the different combinations individually. And when I say combinations, think about the table that we drew before up in this end, the different cells. So we need to be able to handle each cell individually, or we need to be able to have a separate implementation for each of the different cells. So that means that enter will call enter in the gate state, pay will call pay in the gate state, pay OK will call pay in the OK in the gate state, and pay failed will call pay failed in the gate state. And then we decide, not up here in the interface, but down here in any of the concrete states, what the implementation should be for each of these different methods. Again, depending on which state we're in. And that's really it for the UML. There's nothing strange to it. And of course then, the gate needs to hold a reference to the gate state, and then somehow we can change these states. So there are a few different ways of going about how to model the changing of states. And we are going to choose a way in which any particular gate state chooses which new gate state to transition to. And for us to be able to do that, the gate states will need to have a reference back to the gate. So the gate state needs to be able to talk to the gate in order to tell the gate to change its state. Now, if you've seen my other videos, you know how I rant about avoiding mutation. In this video, I'm avoiding the discussion of avoiding mutation in order to keep it simple. So while I'm building methods that mutate state here, if you think about it, you could probably devise a way where we return instead of mutate. So we call a method on the gate, and this method needs to return a new gate which has the new state. So it delegates down to a gate state which happens to be one of these concrete gate states, and instead of that gate state talking to the gate and telling the gate to change its state, what it could do is that it could simply return a new state, right? It would say, well, if you are in this state, you would now be in this state, and then it returns that state which comes back to the gate, and then the gate maybe says, aha, okay, so that's the new state that I should be in, and then it wraps that in a new gate and returns that new gate. But that's if you want to avoid mutation, and we will skip that discussion now. So instead we will say that the gate states have a reference to the gate, and we will add, should have done this first, we will add a method to the gate which is called change state, and it takes a gate state as a parameter, so if we're running out of space. So any of the gate states, whenever they are called, whenever a method of them is called, they may, if they want to, so they can, but can choose not to, change the state of the gate by calling change state and passing a new state. So they would produce a new state and then pass that to the gate, who would then set that as its current state. So the next time we call another method, we would then end up in one of these methods of that new concrete state that it produced. But again, there are different ways of doing this, and this is one. But check out the books mentioned for more examples, and I'm sure you can find plenty of different examples on the internets. Now, let's super quickly look at some example code. Let me remove this stuff. So let's get going. Well, we know that we need a class that's called the gate. And let's build out all the pieces first. And then we know that we need an interface, which is called gate state. Let's open that up as well. And then we know that we need implementors of the gate state. Let me just build one. So we'll build, again, the open gate state. So let me say, and that's a class that's called open gate state. And that implements the interface gate state. Bit crammed here, gate state. Let me open that up. And these are the three parts we need. And of course, again, we would have more classes that would implement the gate state if we were to build the full scenario that we modeled before, or if we were to build the full state machine that we drew up before, the full turnstile. But let's start with the gate. What would the implementation for the gate be? Well, we know that we have these four methods. So we have the method enter, we have the method pay, we have the method pay okay, and we have the method pay failed. And these are all public methods that don't return anything, so we'll specify void. Public void, and public void. And I'm realizing now the indentation got a bit messed up because I'm indenting backwards. This of course should be indented within the class, but I was trying to save space. Apologies for that. Hopefully you can see that this is within the class. And let's say that these take no arguments, none of them. And then we open up the different methods and we need to write some kind of implementation for them. And what are the implementations? Well, the point is, as we said before, that these simply delegate. So the enter method should delegate to a state that it should have. We haven't written this yet, but let's just draw it up. What would happen is that we would say this dot state dot enter. We delegate to the enter method of the state. And then for pay, we would say this dot state dot pay. We delegate. And for pay okay, this dot state dot pay okay. And then for the pay failed, this dot state dot pay failed. And so forth for all of the different methods that we need. But we are now talking about this dot state. And what is this dot state? So we need to define that. So then let's say that there is an instance variable. Let me follow this indentation instead of the class indentation. Again, apologies about that. So we need an instance variable of type gate state, and let's call it state. So it's of type gate state, which is this interface over here. And we call it state, which is the name that we used here in these different methods when we delegated. And then let's specify a constructor. So we have a constructor, so public gate, and in that constructor we pass a gate state. And this will be the initial state. So let's call it initial. Let's open up the constructor. And then in the constructor, we say this dot state equals initial state, in other words, and we'll close the constructor. So this means that when we build a gate, when we instantiate a gate, this gate will be given a gate state. And that gate state will be used as the initial state of that gate. Because we need to have a state, right? If we just set gate state as state, then the state variable would be null and we don't have a state. And then we can't delegate. We can't say when enter is called on the gate, we can't say this.state.enter. It will blow up because enter does not exist on null. So we need to set it to something and we need to decide on an initial state. And again, this varies depending on who you ask or what variation of the state pattern you're using. But I decided to inject this initial gate state through the constructor so that we could instantiate gates with different initial states, with different starting states. But maybe, most probably, you would initialize it with, you would instantiate it with the closed state, so the closed gate state, because probably the turnstile starts as closed and then you have to pay. Or I mean, you could start it open, doesn't matter, then it'd be one for free. Anyways, let's now look at the interface with the gate state. The interface with the gate state will contain 4 methods, and these 4 methods are enter, pay, pay OK, and pay fail, but not for the reason that we've specified them here again, because these are 2 separate hierarchies. Here we don't actually have a hierarchy because gate is a concrete class, but hypothetically we could have a hierarchy of here, of course. But states have a separate hierarchy, but we've just chosen the same names to make our lives easy because we want behavior to vary on the basis of every separate action. We want to be able to handle every separate action and state combination separately. So let's specify that we have these methods. So the interface specifies that there needs to be 4 void methods, and these are called enter, pay OK, and pay failed. And then we need to supply implementations. Sorry, let me close this interface. And then if that's the interface, then we need to specify these methods in all of the concrete classes. And if we are here looking at the open gate state, then this class, because it says or claims that it implements the interface gate state, then this needs to have implementations for all of these 4 methods. Let me also just add these parentheses to show that these methods did not take any arguments. So I'll be rude enough to actually only implement one of the methods, because I'm guessing that by looking at one of them you can figure out how to implement the other ones, because we simply have to follow the transition diagram that we drew before. But let's look at what happens if we are in the open gate state and we receive the message pay OK. So here we would then have a function that's public and returns nothing, so it's void, and it's called pay OK, takes no arguments. So we're implementing this function. And what this would do is that we don't need any ifs or any of that. When we are here, we know that A, the gate is open, and B, we just learned that the payment was okay. So that's a very specific scenario, right? We don't have to think about, okay, but what if the payment is processing and it's not actually okay? Or what if the gate is not actually open, but it's closed, or any of these other things? We know these 2 things. These are 2 facts, right? This is, when we are here, those 2 things are true, because otherwise we wouldn't be here. And this is really the power of replacing a conditional with polymorphism. When you are in that place, you know a few things about reality. So what we need to do is that we need to let the user in. Let user in. I'll just add that as a comment because, again, that depends on what we're actually modeling and depends on your scenario. But here you put the logic that describes what happens when the user moves through the turnstile. But after that, we also need to follow the transition diagram that we drew up here before, or sorry, I should say the transition table that we drew up here before. When the payment is okay and the user has been let in, what we also need to do is that we need to shift the state from open to closed. So what we do is that we say, and here we now notice that we are missing a few things. So we would say this dot gate, referring back to an instance of this. In other words, referring back to the instance that has this state. This dot gate dot change state. And to this change state method, let me open that up and break a line. So I'm on the same line, but I'm writing it as a new line here. And to that change state method, we pass what? We pass a new state which is not of type open gate state, but which is of type closed gate state. So we say new closed gate state. And what do we pass to that constructor? Here you can see the missing piece. To that constructor, we of course need to pass the gate. This dot gate. Close the constructor and close the method call. And then let's close this method, because that's all it does. So we can now see that we're missing two pieces. We said that we have a reference to a gate here in this class, which we don't. And we said that we have a change state method on the gate, which we don't. So let's make sure that we build those two. But before we add those, let's add some dividers to make this a bit more clear. So one here and one here, right? Just to emphasize that these are three different things. And then let's add the missing piece here in the gate state, or in one of these concrete gate states. So the point was that this gate state somehow needs to have access to a gate, because here we're saying this.gate.change state. So what's this dot gate? Well, as usual, dependency injection. What we need is that we need to inject a gate into this class. So we need a constructor here. So public open gate state, because that's the name of the class. And then this takes something of type gate. So gate, due to lack of space, let me just call it G. I'll close the parenthesis here and then open the constructor. Close the constructor here, and then in between I'll write this dot gate equals G. So our instance variable, which we haven't declared yet, but our instance variable called gate should be equal to this G that we were passed in, which is of type gate. So then it's the responsibility of the gate to pass itself into the open gate state when it constructs it. And then of course we need to declare this instance variable of type gate that's called gate. So let me just duplicate this line over here so that we can create some more space. So let's say class open gate state, which implements the interface gate state. And then we open up, right? It's the same thing as this line here, so that I can remove this line here, which gives us a bit more space, which means that we here can add this instance variable of type gate that we simply call gate. And it doesn't have an initial value. But we set this .gate immediately when we run the constructor, because in order to instantiate this open gate state, we need to pass it a gate. So that was the missing piece in the open gate state. And of course, let me just mention again that now we just implemented the payOK method, but of course this class needs to implement all of these four methods, all of the four methods from the interface gate state. So it also needs to implement enter, pay, and pay failed. And then all that stuff we also have to do for each of the different states. We have to do that also for the closed gate state, and we have to do that for the payment processing gate state, or whatever we decided to call that. And that might sound like duplication, but it's not duplication. What is duplicated is essentially the method calls. But in some sense that's very good, because then static typing can help us, or the compiler can help us to enforce whether we have indeed implementations for all of the methods or whether we don't. So in other words, if we would start to build the closed gate state, for example, and we forgot to add the method pay failed, we wouldn't even be able to compile, because pay failed is required by something which is of type gate state. And if we try to avoid having it implement the interface gate state, then we suddenly can't treat that state uniformly as the other states. So whenever we want to change state to that closed state, then we'll get a compiler error there, because it's not of type gate state. So we're sort of locked in a very good way, in the sense that the compiler can help us catch lots of errors. And semantically, it's very, very easy to now reason about the different implementations. Because if you think about it, here we have one of these sort of key methods. This is the thing that we're really after. Like we're saying, what happens if you receive the message payOK when the gate is open? And then we look at all of these different pairs. What happens when we have the state closed and we receive the message pay failed, and so forth and so forth. So semantically, it's very easy to reason about the scenario at hand. But anyways, the missing gate here, upon which we call change state, that was one of the missing pieces. The second missing piece is the fact that we here assume that gates have a method called change state, which actually it doesn't. So let's add that. And this is going to be really crammed. I'm not sure how to fit that in, but let's do this. If we move the divider here, and then I'll just do this dot here, to emphasize that when I write here, it's not a continuation of these lines. I simply mean that this comes after here. I totally ran out of space. But what happens here is that we need to have another method, which is this method called change state. So public, and it's also a void method. So public void, and it's called change state. This was really crammed. Change state, and what are the arguments to that method? Well, so sorry, I'm continuing on another line here. Well, the type of that argument has to be type gate state. Because if we're saying change state, then we need to change to another gate state. So it needs to be of type gate state. Gate state. And to save space, let me just call it S as short for state. We close the parenthesis and open this method. And what does this method do? Well, gate states, those are the states that a gate can have. And when we're saying change state, then we want the gate to change its current state to this new state. So we already have this gate state variable, this instance variable called state, which is of type gate state. So what we do is we simply say this dot state equals S. And S was this gate state that was passed to the change state method. And that's it for that implementation. So that's that method. It simply accepts a state and changes the state of this gate. But that's actually not everything, but because there's one thing that we're missing, and that is that in these concrete states, we said that whenever we create an open gate state, it needs to accept a gate. In other words, the states need to have a reference to the context. So the context has a state, but it's dual. So when the context has a state, it needs to give itself to the state so that the state can tell the context when we need to change state. And again, there are other ways of doing it, but we're just doing it this way now. And I think you can see the point is that under different state and message combinations, we want to change to different states or transition to different states. So in other words, what I mean is that when this open gate state changes state, it instantiates a new state here. So, and then we can see that we here actually pass this dot gate. So new states created by this particular gate state will be fine. They will have a reference to the gate. But the question is, the first one, the first open gate state, how did it receive a reference here to the gate? Who instantiated that? And the problem here is that we here previously made the assumption that the class gate will have an initial gate state passed into it rather than it instantiating itself. So the problem here is that we can't really dependency inject the gate state, the initial gate state, if this initial gate state is supposed to have a reference to the thing that we are dependency injecting it to, right? We are instantiating a gate, and the state of this gate needs to have a reference to this gate that we are instantiating. So we can't build the gate state before if we are supposed to dependency inject the gate into the gate state. We could if we mutate in the gate state. If, let's say, we either say set gate on the gate state. I think generally that's a pretty bad idea, so try to avoid doing that. But we could do that. And the other alternative would be that we simply pass the gate to the gate state whenever we call one of these methods from the gate state interface. So whenever we call enter, pay OK, or pay failed, we would also supply the gate. So if you think about it, that's actually not a crazy idea, because then we can actually specify on the interface level that these methods necessarily needs a reference to a gate. But then, of course, maybe that isn't the case for all of the gate states, because maybe some of the states don't change the state and then don't actually need a reference to the gate. Because again, the point of having a reference to the gate is that we want to be able to call change state on that gate. And if we don't need to change the state, then we don't need a reference to that gate. And then we would simply, for no good reason, have to pass in an argument to that method, even though we're not using it. But again, I think you can experiment with this and see that there are a lot of different ways we could do it. Now we'll just do it in a very simple manner. Instead of dependency injecting here, instead of passing the gate state in that we called initial here, instead of passing that in through the constructor, we'll just have an empty constructor, open that up, and instead of saying then that this dot state is equal to this thing that we were passed in, we can't do that, right? We said we can't do that because it needs a reference to this instance that we are now in the process of constructing. So we need to first construct the instance, and then we can give this instance to the state that needs to have a reference to this gate. So instead of saying that it equals this initial dependency injected state, we will simply build a new state, and then let's say, then we're back into the question of what is the default state. So maybe the default state then we specify here is a new closed gate state. And to this closed gate state, let me move this divider a bit. To this closed gate state, we pass this. So when constructing this new closed gate state, we give it a reference to ourselves. We give it a reference to this gate. So the gate ends up here, and we set it to the instance variable, which means that we can then call change state on this gate. For clarity, let me just add the dotted lines here to show that these are two separate pieces, or this is the continuation of this class. And if you've been watching my other videos, you know how much I like dependency injection, so I'm not super satisfied with the solution that we're instantiating the state here, but feel free to experiment with the other solutions that we alluded to, and feel absolutely free to post something in the comments if you think one of these particular solutions is better, or if you find a new solution. Let's quickly recap before we wrap up. Let me mention one more thing. When we injected a gate here to the open gate state, that's when I really felt the feeling that maybe gates should actually have their own inheritance hierarchy. So just remember the saying, coupled to interfaces, not to classes. Coupled to abstractions, not to implementations. To abstractions, not to concretions. So here we are coupling to a concretion. We are coupling to a concrete class. But in order to stay a bit more flexible, it would be very simple for us to just say that gate is actually a concretion, is actually a concrete class that implements an interface which is gateness, or which is like, or something which is something that is like enterable and payable. And maybe that would actually be like, maybe we would actually call the interface gate. But I think it would make sense to just add that interface and make sure that the gate then says that it implements that interface, so that here in the states we don't have to accept gates. We could accept the more general type. We could accept gates, or in other words, the interface for gates, whatever we call that. Just a side note. But now, let's quickly recap before we wrap this up. So we've got three things on the board. We've got the class gate, we've got the interface gate state, and we've got a concrete class called open gate state, which implements the interface gate state. So gate is the turnstile. It's the thing that we want to move through. It's the thing that can have states. And gate state is the definition of what it means to be a state, of what it means to be a state that gates will have, that turnstiles will have. And then open gate state is one example concretion. You remember we had 2 in the beginning and 3 in the end. Open, closed, and then open, closed, and processing. And here we just have one example, which is the open gate state. And this again implements the interface gate state. And whenever we produce a gate state, we run this constructor. And there is only one constructor, and this constructor accepts a gate. So whenever you produce a gate state, you need to give this gate state a reference to the gate it is a state of. And again, there are some slight nuances between different versions of the state pattern, so you may or you may not do that. But in this case, we're doing that. And then we assign this gate that we were passed in to an instance variable. So we say this.gate equals the g that we were passed in. And then this gate state has a number of methods in this blue box here. A number of methods, and here we're only showing one. So let me just say ... here to emphasize that this is not just like you might have other responsibilities for this open gate state, but I'm specifically trying to say that we would also implement enter, pay, and pay failed. Now we're only showing the implementation for pay OK, but because it is a gate state, or because it behaves as a gate state, we need to implement all of these 4 methods. And the point is then that every combination of a state and one of these messages, one of these methods, every combination of one state and one method, one pair of that, makes up or can have a separate implementation. So we ask ourselves, what happens if we receive the message that the payment failed if the gate is closed, or if the gate is processing the payment? And then we have a specific location in which we can put that specific code. And that specific code is essentially here. So in this particular case, we were looking at the combination. What happens if the gate is open and we receive the message pay OK? And also now I realize, sorry, my mistake. This would hold then for the first state scenario we drew. When we had closed and open, and you could go from closed to open and from open to closed. So let me just put a C here to denote closed and O here to denote open. Because then we were saying that if you receive that the payment is okay when it's closed, you move to open. Sorry, I forgot about this. But then we made it a bit more complex and we added the processing state. So if we also had the processing state, then we said that, well, you can't open if you receive the pay okay message when you're in closed. You need to first be in the state processing so that the system knows that it's actually awaiting or waiting for a payment okay message. It's actually waiting for the payment processor acknowledging that the payment actually went through. So sorry, this was a bit inconsistent. So this holds in this simplified example when we go from closed to open and from open to closed. And of course, we can stay in closed and we can stay in open. But sorry about that. So the implementation would be different if we are also considering the processing state that we had before. Because then if you receive a pay okay in open gate state, we would simply not change the state, which then probably would equate to us doing absolutely nothing here. This method would just be empty. Because we would say that, well, if you receive the pay okay message when the gate is open, and we only really want that message when it's in the processing state, then here we do nothing. Unless you are building that other architecture that we talked about before, where we're trying to avoid mutation. If you're building that architecture where states are returning new states and gates are returning new gates, then this gate would still have to return something, because it can't just return nothing, because then we have nothing to wrap when we get back here. But then we would simply return a new instance of an open gate state. So then it's really like this sort of recursing arrow. So staying is also an action. So it's not like we would do nothing, which we do now in the mutation case, but if we would try to build this sort of immutable gate, then we would here simply return a new state, which is also an open gate state. But anyways, that's if you're trying to follow that kind of architecture. But that's it for the open gate state. And then again, we would have a closed gate state and a processing gate state. And then here, over here, we have the gate. And the gate is, again, the turnstile, the thing that we are actually interacting with from the outside. And we can ask it enter, pay, pay okay, and pay failed. So we can try to enter it. We can try to initiate the payment, and probably we would take a card here or something like that as an argument to this method. I mean, we're glancing over lots of details because, of course, we're not thinking about how this payment would actually happen. But again, those are details depending on your scenario. So we have the pay method, and we can call pay okay and we can call pay fail. And these are actually a bit more like events. So maybe these should actually be called on payment okay and on pay failed. So as in, like, these are things that can happen. And these would probably not be called by us from the outside when we're sort of directly interacting with the gate, but probably be called by the payment processor. So pay probably initiates the payment processor, and then the payment processor would call either pay okay or pay failed whenever it receives an answer as to whether the payment was actually paid or failed, or okay or failed, essentially. And these four methods, enter, pay, pay okay, and pay failed, essentially have the same, quotation marks, implementation, because what they do is that they say this dot state, this dot state, this dot state, and this dot state, dot some particular method. And the method we call is essentially the method with the same name as the method that was called here. So when we call enter on the gate calls enter on the state. When we call pay on the gate calls pay on the state, and so forth. So we're just blindly delegating downwards. And again, depending on your scenario, you might have more logic here, or you might have methods that don't have exactly the same name. So maybe enter calls something which is like open in the gate, or something like this. I'm just emphasizing that, again, this is a different hierarchy than this over here. So the names could be different. But in a very simple scenario, it's probably one-to-one. So one method in the gate is one method in the gate state. And then we just blindly delegate. And of course, the last piece is that we have this method change state in the gate. And this change state method accepts something of type getState, we here call s, so that we can take this s and put it inside the instance variable this.state. So what I didn't mention before is that the constructor of this gate simply takes no arguments but sets the initial state itself. So it instantiates a new closed gate state. So it says, well, whenever you instantiate the gate, it will necessarily start in the closed gate state. So let me instantiate that, pass myself to that gate state, and then set this to this.state. So I'll set it to the instance variable, or I'll put it inside the instance variable of type getState, which is called gate, within this gate. So now the gate has a reference to its own state. So whenever we were saying here that we delegate to enter, delegate to pay okay, and to pay failed, that happens on the state polymorphically. So the state from the context of gate is of type getState, of this general type getState, of this interface. But of course, we can't instantiate interfaces, so when we say this.state, the state will happen to be any of these concrete states. And we've said, or we know that initially it will be the closed gate state because we manually instantiated that. But what happens after that, we don't know at this point, and that's an effect of the implementation of these different methods in the concrete states, because they can call change state and change the state to some other state, which also of course implements the interface getState. And here's the polymorphism, so that the next time we call one of these methods, in some sense we're not sure which one concrete state we will call them in. But it will be a concrete one. But again, which one it is determined by which state we were in before. And that's when, at least I find it helpful to think in terms of these state machine diagrams. So we draw up the different states, and then we draw arrows between them. We say, okay, from every state I can receive any of these possible messages. Firstly, what are my states and what are my messages? And then we just draw them up. We say, here's my state, these are the messages. Where do these arrows take me? Sometimes you just stay in the same state, sometimes you actually move to another state. And when you then move to another state, this is when we instantiate another state, another gate state, and pass that to the method change state, so that we actually change the state of this gate. And that's how we're sort of traversing around in this state machine, and so forth. So that's all I had to say. Hopefully you now feel that you have some grasp of the state pattern. If you have any questions or comments or want to discuss something, shoot that in the comments. Beyond that, links to both of these books are in the description. Remember to subscribe if you want more videos like this, and if you appreciate any of these videos, feel absolutely free to share them with any of your friends. Beyond that, thank you super much for watching, and I will see you in the next one.